Now see here, in this chapter we will study here behavior of perfect gas and kinetic theory. Now see here, according to Dalton's, each and every element is made of atoms. So we can say atoms are the smallest constituents of element. You know, one element has got the same types of atoms, but if you take the elements, different elements, they have got the different types of atoms. Now we have done the three states of the matter, like a solid, liquids and gases. You know, in the solids, all the atoms or molecules are tightly bound with the strong intermolecular forces, whereas in the liquid they are bound here with the comparatively weak intermolecular forces, but in gases intermolecular forces are very weak. So now see here, we are going to discuss here about an ideal gas or a perfect gas. So what is an ideal gas or perfect gas, and what gases are considered as an ideal gas? So now see here, ideal gas or perfect gas here. An ideal gas strictly obeys, that means an ideal gas or perfect gas strictly obeys gas laws. Gas laws are there. First one is the Boyle's law, Charles law and Gay-Lussac's law. So these are the three basic gas laws. So all the ideal gases here obey all these three gas laws strictly, and one, there are the main characteristics of the ideal gases. So see here, the size of the molecules of the ideal gases are taken as 0 size, it means they are taken very small molecules, and also here the intermolecular forces between intermolecular forces in the gases or in the ideal gases, that is here very weak, that is, it means there is no interaction between the molecules in ideal gases. Perfectly, there are no gases which are ideal here, but certain gases at low pressure and high temperature can be considered as ideal gas, like a hydrogen, nitrogen or oxygen. These gases can be considered as an ideal gases here. Now see here, behavior of gases or at low pressures and high temperatures, the gases follows this relation PV is equal to KT, where P is actually pressure and V is volume and T is temperature. Now P, V and T are pressure, volume and temperature, and where K is constant for the given volume of the gas, and this K can be written is equal to NKB, where N is the number of atoms or molecules in the sample of the gas and Kb is the Boltzmann constant. So Kb can be written here, that is a Boltzmann constant, and its value is given here 1.38 into 10 raised to power minus 23 joule per Kelvin. So we know the K is equal to this. So from here we can write here now PV is equal to NKBT. Now if you write this relation, suppose for the two different gases, so we can write here in this case so we can write here for the two different gases if you are taking, so we can write P1 V1 upon N1 T1 is equal to P2 V2 upon N2 T2 is equal to Kb. It means this thing is here constant because the value of Kb remains constant. So if you are taking P1 V1 and T1, if temperature remains constant or remains same, then we can also say N1 is equal to N2. So here from this relation it is clear that if P1, V1, T1 are same or the constant, so we can also write here N1 is equal to N2.